magnetic flux density in the middle of a circular coil using Biot-Stafford law. So if you use Biot-Stafford law to find out the magnetic flux density here, you have to divide this coil of wire into an infinitesimal small current element, dl, and then you want to sum up all this dl around the coil and work out the contributions. So looking at the center of the coil, you find that they are of equal distance from the coil, and therefore we can conclude that the magnetic flux density at the middle is contributing from all the current elements is of the same magnitude. And therefore we can apply Biot-Stafford law by assuming this to be a small straight line wire, very small straight line wire. My current elements dB will be equal to mu naught I over 4 pi dl over a squared, and that is for a small current element along my circular coil. And to find out the overall at the midpoint, so we basically sum around the circle. So to integrate over dl over a circle, that will be equal to the perimeter of the circle, which is 2 pi a. Okay, so basically so B will be mu naught I over 4 pi a squared, all these are constants, integral of dl over the circle, and this part here is 2 pi a, and that will be equal to mu naught I over 4 pi a squared times 2 pi a. A and a squared cancelled, 2 will be 2, and then pi and pi cancel. That end up with mu naught I over 2a, and that is the magnetic flux density at the middle of the coil. Right here will be equals to mu naught I over 2a. Okay, that's only true at the middle of the coil. So if you have n number of coils, then the magnetic flux density will be multiplied by n. And then if you move off axis by distance x, then the flux density at this point for a coil of n turns will be equal to mu naught n times I a squared over 2a squared plus x squared to the power of 3 over 2. Okay, so meaning that this is my coil. This is where at the axis, and then if you move away at the distant x, this will be the magnetic flux density going away along the x direction. I'm not going to show how this equation come about. If you're interested, you can look up in the electromagnetic textbooks. They will show you how this can be derived. Okay, so this is the profile of the magnetic flux density. This is right at where, so if this is my coil, looking at the side, if you're moving away x from the coil, and this is how the magnetic flux density decreases from the coil. So if x is much greater than a, then you find that the magnetic flux density is proportional to 1 over x cubed. And if you remember, when we talk about electrostatics, we have electric dipole, which has the same profile. So if you have a charge plus and minus charge, and then if you have x far away from that charge, you find that that also decrease with a distance of x cubed. Okay, so this is similar to a dipole. So in effect, if you have a circular coil of wire, that itself is called a magnetic dipole. A circular loop of current is called magnetic dipole. And if you have, I'm not sure whether you studied this, if you studied property of materials, you know that we have an atoms, and then you have an electrons that going around the atoms. Yep, so you have electrons going around the atoms. So electrons moving that is equivalent to a current in the opposite directions. So this itself is called a magnetic dipole moment of your atoms. So in materials, you have all these electrons rotating, so your materials also have magnetic dipole. But in the normal materials, these orientations, so if I have a materials, so the dipole moment is in all directions, so normally it cancels out. In magnetic materials, they are aligned in a particular direction. So it gives rise to a particular magnetic field, like your permanent magnets. Or in conducting materials, you can apply a current, and all this will align in a particular directions. And then you can make the materials to become magnetic. So circular loop of currents is a magnetic dipole. Similarly, in your atoms, with the electrons rotating the atoms, that also equivalent to a magnetic dipole as well. Typical value of magnetic flux density, strong permanent magnets is about 1 Tesla. Superconducting magnets can go up to 20 Tesla in DC and can go up to 50 Tesla if we use a pulse. The Earth magnetic field or magnetic flux density is 1 to 10 to minus of 4 Tesla, and then a neutron star that is hundreds millions Tesla. Okay, so but 1 Tesla is actually quite a large field and is not normally encountered in our everyday situations. So sometimes the magnetic flux density also called in the unit called Gauss, and the relationship of Gauss to Tesla is 1 Gauss equal to 10 to the power minus 4 Tesla. Okay, so 1 Gauss is roughly about the magnetic flux density of the Earth field. Okay, so that is an example from Bayer-Stafford law that we have looked at last week. In Ampere's law, so there's another law called Ampere's law. This is, can think of this as the equivalence of Gauss' law in electrostatics. And hence the Bayer-Stafford law will be equivalent to your Coulomb's law in electrostatics. So Ampere's law is easier compared to Bayer-Stafford law, because Bayer-Stafford law just now you look at, you need to do integrations over all the current elements to find out the contributions. The example we'll consider in this module, we'll look at inside and outside of a straight wire, inside a long solenoid, within a coaxial cable, between a pair of parallel current sheets. Okay, so these are the things that we'll look at in this module. So what is Ampere's law? So Ampere's law states that the closed loop integral of the magnetic flux density dot the loop is equals to mu naught I. So our Gauss law is equals to the charge enclosed. So this is Gauss law is a closed surface integral, so which means that it's a bubble, closed surface. Here is a closed loop integral, which means that if you draw a loop around a certain things, then the magnetic flux cut through that loop will be equals to the currents. So the line integral of the magnetic flux around any closed loop is equals to times the total currents threading through the plane of the loop. So mu naught times the total current threading through the plane of the loop. So that is Ampere's law. So the loop is just a mathematical construct, which means that there doesn't have to be a physical representation. You can draw anything around the current. Equations 7 only allow us to find the magnitude of the magnetic flux density, and then the direction has to be found using your right hand rule. To evaluate magnetic flux at any point, the loop must drawn the loop drawn must pass through that point. If I want to find the magnetic flux at this point, then my loop must pass through this point. Okay? So I can't draw a loop like that to find the magnetic flux at this point. Select a loop that is convenient, that is coincide with the length of the magnetic flux density. So you have to have a prior knowledge how the magnetic flux looks like before you can apply the Ampere's law. So for example, a long current wire, we know that the magnetic flux is going round this wire. So you have prior knowledge knowing that my electric flux, my magnetic flux density is going, or magnetic flux is going round this wire. So if you choose the loop to coincide with the magnetic flux line, then you make the integrations a lot simpler. Okay, so for a long straight wire, we know that the magnetic flux is going around the current wire. So if we choose the loop to coincide with the magnetic flux, then the magnetic flux density B will be constant around this loop. Okay, so our Ampere's law is B dot dl is equals to mu naught I. And if you choose this loop to be coincide the magnetic flux density, then magnetic flux density will be constant around that loop. And therefore we can take B out of the integral. And therefore this integral simply the length of the loop, which is the perimeter of the circle. Okay, so that integral will be 2 pi r. So all points on the loop have the same value of B since they are all equidistant from the wire. The direction of B is given by the right hand rules, and applying Ampere's law, we can take B out of the integral, and this integral simply equals to 2 pi r. And that is equals to mu naught I, and therefore my magnetic flux density will be equals to mu naught I over 2 pi r, which is the same results that we obtained from Biot-Stafford law. Okay, so that is Ampere's law. So we're going to apply this to a long cylinder wire, non-magnetic. So if we have a long cylinder of wire carrying a current I, then we can find out the magnetic flux density profile in the vicinity of this long cylinder wire. Okay, we can divide this into two problems. One is inside the wire, which is the conductor, and the other one is outside. The outside one, we have done that just now. So if you have a straight wire outside, we find that B is equals to mu naught I over 2 pi r. Okay, so we've done that for outside, for r greater than A, which is on the outside. The magnetic flux will be mu naught I over 2 pi. But we can also find the magnetic flux density inside the wire itself. So the overall current on this wire is I. Okay, so you can find out what is the current at a distance r from the center in terms of current. So we have the overall current, loop current, is equals to I times pi r squared over pi a. Okay, so this is assuming that overall my distance, my area here, pi a squared, has a current I. So the current density is I over pi a squared. Okay, so current density, current over the area of my wire. Okay, so the current is I, overall area is pi a squared. So if you want to find out what is the current over this area, that has a radius r, so that area will be pi r squared. Okay, so that currents over this profile, that will be I, the current density, times that area, pi r squared. So if I draw my Ampere's loop around this, so that will enclose the currents of I, pi r squared over pi a squared. Okay, so if I draw, so let me recap. If I have my wire, if I draw an Ampere's loop outside, that the currents that pass through this loop is I. Okay, so this is a current I. If I draw a loop that is inside the wire, now the total, it would not have the overall current I, but only a fraction of that current. Okay, so to find out what is that fraction of current, you take that area, which is pi r squared, times the current density, which is I over pi a squared. And that will be the currents that going through my loop. So you simplify this, pi and pi cancel, this will be I r squared over a squared. And then you apply your Ampere's law. Mu naught, so now it's not just I, the currents will be I r squared over a squared. This side here is still the same because you draw the loop over the magnetic flux line, and therefore B is still constant, and then this will be 2 pi r equals to mu naught I r squared over a squared. And then simplify it, you find that the magnetic flux density inside the wire will be equals to mu naught I times r over 2 pi a squared. Okay, so outside wire, we find that B is proportional to 1 over r squared. Inside the wire, it's proportional to r. Okay, so you can draw the profile of how this looks like, and the profile looks something like this. So this is my cylinder wire. This is the center. 0, go linearly up. As we go, the magnetic flux density increases linearly until it peaks at the surface of the conductors, and then outside it starts to decline at a rate of r squared, or distance squared from the center of the wire. Ampere's law allows you to work this out, okay, very easily. So all you need to do is apply Ampere's law outside, and then inside you need to calculate what is the fraction of the currents in the wire. And then the direction, you can use your right hand rules to work out the direction of the magnetic flux density. So that is on a long straight wire, a long solenoid. So solenoid is something like this. If you take a cross section of that, looking over this distance, on the top, you see that the current is flowing into the page. No, on the top is flowing out of the page, and then it's going into the page at the bottom. Okay, so that is, if this is my solenoid, basically I cut it right at the center. You see that on the top, current coming out, and then flow back in at the bottom. And solenoid is quite widely used in electronics, especially to use as an inductor. So you can see that the magnetic flux is mostly concentrated within the solenoids, and outside the magnetic flux is approximately 0 because you have contribution from a current going out of the page and a contribution from into the page, and therefore they more or less cancel out each other outside the solenoid. So consider the solenoid shell with circular cross sections, length L and number of turns N. So for long solenoids, B is almost uniformly within the solenoid and 0 outside it. So these are approximations, but it's a pretty good approximations if we have the length of the solenoids much longer than the radius of the solenoid. So applying Ampere's law, B dot dl will be approximately equals to B times L equals to mu naught N times I. So N, because we have N number of turns, so which means that you have N number of current. And therefore the magnetic flux density for a solenoid is approximately equals to mu naught N times I over L. And L is the length of the solenoid. And if we define N over L as the number of turns per unit length with a small letter n, then we can reduce this to mu naught N times I. And that is the magnetic flux density inside a long solenoid. This is another example. So long solenoid, magnetic flux density is mu naught N times I over L, or mu naught small letter n times I. Long wire is mu naught I over 2 pi r outside the wire, and that's mu naught I times r over 2 pi a squared inside the wire. Parallel plate. So we have looked at parallel plate capacitance in electrostatics. So now we're going to look at the magnetic flux density. So if you assume that we put a voltage between our parallel plate and put a load N at the other end of our parallel plate transmission lines, we assume that if you do that, there will be some current flowing in the plate. And if we have current flow, then we have magnetic flux density. Look at the cross sections of this parallel plate. Cross section meaning that across these directions, you can see that you have currents flowing in one direction on the top and current flowing in the opposite direction at the bottom. And again, this looks like a similar profile of what we have looked at just now in the solenoid. Again, we said that the magnetic flux will be uniform within that plate and then approximately 0 outside the plate. Okay, so again, applying Ampere's law. So B inside the plate, and the integral of that will be over the width, W. So if I draw my Ampere's loop, so only this part here, approximately this part here, we have the magnetic flux. And therefore my B dot dl integral is approximately equals to B inside the solenoids times the width of the plate. And that has to be equals to mu naught I flowing on the plate. And therefore we work out that the magnetic flux density inside the plate is approximately equals to mu naught I over W. Okay, so that is for parallel plate. Applying Ampere's law to find out the magnetic flux density. Coaxial cable. Coaxial cable, if you still remember, have an inner conductor and then an outer conductor. So again, if you put this over a supply, over the other end, put it to a load, and then you have a current flow in the inside conductor and a current flow backward in the outer conductor. And therefore we can apply our Ampere's law for the radius r greater than B outside the coaxial cable. So if I draw a loop outside my cable, you find that there will be a current in these directions and then equal currents in the opposite directions. Therefore, if I apply my Ampere's law, mu naught I is 0, and therefore B will be 0 outside the coaxial cable. Okay, because we have one current going in one direction and another current in the opposite directions, and therefore we end up with the magnetic flux density outside my coaxial cable will be equals to 0. And we have done something similar in electrostatics. We find that the electric flux density outside our coaxial cable is also equals to 0. Inside The inner conductors, we have find that in a long carrying wire. So we have done that just now. Okay, that will be equals to mu naught I times R over pi A squared. That is for R smaller than A. And then for the distance between A and B, and that simply equals to our magnetic flux density of a long wire, mu naught I over 2 pi R. Okay, so your coaxial cable is very similar to a long wire carrying a current, except that the magnetic flux density is only finite up to the outer conductors. If you go beyond the outer conductors, then the magnetic flux density will become 0. So just now we find that the magnetic flux line is going around. Previously, we find that the electric flux density okay, so what we have shown that the electric field and the magnetic flux density is always perpendicular to each other. So at every point here, so this is my E or D, and this is my B. And they are always orthogonal to each other or perpendicular. Okay, so that is Ampere's law. So we have been talking about magnetic flux density B. As I mentioned at the beginning of this topic, there is another parameter called magnetic field strength. I said that this is equivalent to our electric flux density, and then we have this is equivalent to our electric field, or H is more appropriate to refer to as the magnetic field rather than B. And the relationship between H and B is B equals to mu R mu naught times H. Similarly, in our electrostatics, D equals to epsilon R epsilon naught E. And the mu R is called the relative permeability, and then mu naught is the permeability of free space. So for most materials, mu R is equals to 1, except that for a few materials that have high mu naught, they are called magnetic materials, things that you use for your transformer. So if you, I don't know whether you see a transformer, you have a core and then you have wire around it. So that iron core has mu R that is maybe in the thousands. Okay, so you can see that what it does, if I have mu R equals to 1,000, then it will increase my magnetic flux density by 1,000. Okay, so if you use compared to a mu R of 1, so you can increase the magnetic flux by using magnetic materials. So here is that magnetics equation 12 is invalid for permanent magnets, but we're not going to go into that. In our discussion, we always assume that equation 12 is always valid. So the relationship between B and H is always governed by that equation, B equals to mu R mu naught H. In this module, when you want to find B or H, you can always apply this relationship. Okay, so we're not going to be concerned about this thing here. So in magnetics, B is the physically meaningful property, whereas in electrostatic, E is the physical meaningful property, whereas H here is introduced to make things easier for magnetic materials. Similarly, in electrostatic, D are introduced to handle dielectric materials. In free space, in non-magnetic materials, almost all dielectrics and many common metals like copper, aluminum, and brass, we have mu R equals to 1. And therefore, B and H is only a scaling factor of mu naught. So you can interchange between the two by just keeping in mind the factor between them. The SI units of H is amperes per meter, and then the SI units for magnetic flux density B is in Tesla. And if you apply Ampere's law using H, then it will be equals to I instead of mu naught I. Originally, we talked about B dot dl equals to mu naught I, and then we said that B is equals to mu naught H. So if I substitute mu naught H dl integral, and that leads us to integral of H dot dl equals to I. For some ferromagnetic materials, i.e. soft irons or ferrites, we can have mu r in the excess of thousands, and that are normally used as a core for your transformer or any other inductive applications.